Good morning to everyone. So good morning. Okay. So immediately I will start with the class. Fine. So that means discussion about previous this one I will have to discuss. So what we have discussed in the last class, lots of disturbances were there. So we have discussed about elements of group 70, right? So which are also called as halogens. So that is because they are salt formers or producers. So that's where we have NaCl, sodium chloride, which is a salt. Fine. So that's where we have the group 17 elements, which can also be called as halogens. Then we have discussed about electronic configuration along with their atomic number. Now when it comes to group 17, which is the radioactive element, so that was astatine, right? So astatine was the one which was radioactive element. Fine. So that's what we have discussed in the last class. 1 minute. So that's what we have discussed in the last class. So when it comes to astatine, which is a radioactive element, so we are not going to discuss about this element for with respect to chemical properties and all. So we are going to discuss about all the other elements like fluorine, chlorine, bromine and iodine. Now when it comes to these elements, outer electronic configuration will be NH2 NP5. So they have the outer electronic configuration as NH2 NP5. Now when it comes to fluorine, N will be equal to 2, right? So when it comes to fluorine, N will be equal to 2. Please remember NH2 NP5 is general outer electronic configuration for group 17 elements. Now when it comes to fluorine, N will be equal to 2. If I take chlorine, N will be equal to 3. If I take bromine, N will be equal to 4. If I take iodine, N will be equal to 5. Like that, the number will goes on increasing because we are moving down the group. We are moving to the next energy level with respect to next period. So that's where we have the general electronic configuration. Now when it comes to energy level 2, there is availability of only S and P subshell. When it comes to N is equal to 3, there will be availability of SPD, right? So after that, next energy level we are going to have SPDF also. Here also we can have the SPDF. Availability I am talking about. Availability of the energy level. I am not talking about electronic configuration. I am talking about availability of the energy level with respect to respective energy levels. Fine? Okay. In that case, when it comes to F, there is no availability of the D subshell in that outermost shell, right? So when it comes to F subshell, there is no availability of the D subshell in the outermost shell. But when it comes to chlorine, yes, it is available. When it comes to bromine and iodine, there will be availability of even F subshell. D subshell is available. Even F subshell will be available. That's what I mean to tell. Fine. So this is with respect to general electronic configuration. Since NH2 NP5 is there, to attain NH2 NP6, that means octet state, it requires 1 electron. It can easily take up 1 electron. That's where we have the -1 as the common oxidation state. -1 will be common oxidation state for the halogens. Fine. Now same way, we have other oxidation states like +3, +5, +7. But when I am talking about positive oxidation state, fluorine is not going to show positive oxidation state. it will show always -1. But when it comes to chlorine and all, they can show. So when it comes to chlorine and chlorine, bromine and all, then it can show the positive oxidation state when they are bound to oxygen or fluorine. So which are much more higher electronegative compared to these elements. But fluorine is the highest electronegative element. Right? So that's where always whether oxygen is there or any other halogens are there, but still it will always go with the -1 oxidation state. Whether I am clear? All of you have understood? So that's where we have discussed about oxidation state in the last class, group 17, oxidation state. Now we will come to next one. That is with respect to some of the properties which we have discussed. Now when it comes to electronegativity, all of us we know that electronegativity is nothing but pulling the electron towards itself in a covalent bond linkage, or when two elements are linked with each other by the covalent bond, they will attract the element towards one particular element. That's where it is called as electronegativity, not accepting, not taking within its shell. It is just attracting. So that's where we have the electronegativity. And naturally fluorine with a Pauling scale of 4. Right? Pauling scale does not have the unit. Okay? So Pauling scale of 4. It is the one which is an highest electronegativity value according to Pauling scale. Fine? So that's where we have the fluorine. Now, with respect to electron gain enthalpy. Now, what do you mean by electron gain enthalpy? Electron gain enthalpy means amount of energy released when an element is going to take up the electron. So electron gain enthalpy means amount of energy released when an element is going to take up the electron. That's where we have the electron gain enthalpy. Fine? Now when it comes to electron gain enthalpy, chlorine is going to dominate. When it comes to electron gain enthalpy, chlorine is going to dominate. Okay? When you consider electron gain enthalpy value. So that means what I mean to tell you is chlorine will have highest negative electron gain enthalpy value. Chlorine will have highest negative electron gain enthalpy value. I am talking about highest negative. That means it can accept the electron more easily even compared to fluorine. Fine? All of you have understood? So electronegativity wise fluorine. But when it comes to electron gain enthalpy, it will be chlorine. The reason is very simple. When I am talking about fluorine, so we have nucleus and outermost energy level is 2. In case of the fluorine, outermost energy level is 2. So now in outermost energy level, how many electrons are there in fluorine? In outermost energy level, how many electrons are there in fluorine? Can any one of you? Yogesh sir. Okay, it is 7. Okay, so that's where 1, 2, 3, 4, 5, 6, 7. Right? Now if the same thing if I do it for chlorine. So where energy level is 3, outermost energy level will be 3, 1, 2, 3, 4, 5, 6, 7. So what I mean to tell you, you can see here there is a huge crowd of electrons. In a small space, there is a large amount of electrons which are already present. So now due to that what will happen? So due to that another one electron when it will come. So there will be electron repulsion will take place. Electron repulsion will take place. Due to that, fluorine is not going to take up the electron easily. It cannot take so easily. So this is one thing you should remember with respect to electron gain enthalpy. Fine. So now when it comes to chlorine, since there is enough space for another one electron to get accommodated easily. So therefore, to attain the octet state, chlorine will take up the one electron easily. It can accommodate that one easily due to large size of the outermost shell. So that's where we have the highest negative electron gain enthalpy for chlorine. Now, in that case, why fluorine is then highly electronegative? That is because of its small size. High electronegativity is due to the small size. Fine. So I will write here why fluorine is highly electronegative. That is due to its smallest size, atomic size. Due to that, nuclear force will be more. Due to that, nuclear force will be more. So that it can attract the one another electron which is near to that. It can attract, but it will not take in its shell. So that's where we have the smaller size which will make fluorine highly electronegative. And smaller size will make fluorine to have highest ionization enthalpy. I am not talking about group 18. So highest ionization enthalpy. So that's where smallest size is the one reason for the high electronegativity and highest ionization enthalpy for fluorine. Now, small size is the only reason. Smallest size is the only reason for electron repulsion, which makes it to have less negative electron gain enthalpy. Which make it to have less negative electron gain enthalpy compared to chlorine. Whether I am clear? All of you have understood? Let me know all of you have understood. Okay? All of you have understood? Okay. So what I was telling here is, when it comes to fluorine, due to the smallest size, it is having highest ionization enthalpy, where it will be difficult to remove the electron from the outermost shell. Next, electronegativity will be also high due to the smallest size. And due to the smallest size, there will be electron repulsion, which makes accepting the electron difficult also. But when you have the question that, why fluorine, although it is highly electronegative but has less negative electron gain enthalpy compared to chlorine, then your answer should be, due to the smaller size there will be electron repulsion, which makes fluorine to accept the electron less efficient compared to chlorine. That should be your answer. One word should be smaller size and another word should be electron repulsion. Better to put that word also. Along with smaller size, put the electron repulsion. That word should also come when they have asked the question about electron gain enthalpy. Now, if that is the case, another major property which is going to have effect due to the smallest size of fluorine here is bond dissociation enthalpy. Because all of us we know that group 17 elements normally they will be in a diatomic state. They will be present as diatomic state. Now we have fluorine. Naturally, fluorine should have the single bond. Fluorine. Even same logic. Fluorine, single bond. Same logic. If I take bromine, it will be a single bond. When it comes to iodine, it will be a single bond. Right? At room temperature, these two will be present as a gas. At room temperature, it will be present as a liquid. At room temperature, they will be present in solid state. Fine. So that's where we have the physical form. When it comes to fluorine, it will be yellow color. It will be yellow color. When it comes to chlorine, yellowish green color. That's for its name is chlorine. Yellowish green color. When it comes to bromine, it will be red color. And when it comes to iodine, it will be violet color. That's for iodine name. Fine. So that's where we have fluorine, which will be yellow color. Chlorine, it is due to yellowish green color. And bromine, red color. And iodine, violet color. So chlorine and iodine, name itself indicates their color. Okay. So that's where we have the physical state. Now what I was telling here is there will be presence of a single bond. And very important question, you should give me the answer. So why halogens or group 17 elements will be in a diatomic state in their elemental form? Any answer? Why they should be in a diatomic form? Fast. Why this group 17 elements will be in diatomic state? That is the question. Any one of you? Why they are in diatomic form? Okay. Valency got 8. Very good. So therefore, they will be having single bond and they will be in diatomic form to attain the octet state. Very good answer. To attain the octet state. Yes, Kritik. Even Purnima, you people are absolutely right. So attain the octet state, they will be in the diatomic form. Now I wanted to tell here is when it comes to fluorine, when they are in diatomic form, right? When they are in diatomic form, if I want to separate them, I have to break this covalent linkage. Same logic. Chlorine, I have to make them separate means I have to break this covalent linkage. Now, due to the smallest atomic size, this is one fluorine, this is one fluorine. Imagine. So many electrons, they are present, right? So there are so many electrons which are present. It is too much crowded. So due to that, what will happen? These two electrons which are involved in sharing. So due to the closest approach, there will be repulsion. Between these electrons. So due to that, this bond will become weak. Please remember, although bond length is less, but still bond strength is very low. Although bond length is less, but bond strength is low. Right? So bond length in case of the fluorine molecule, it is very shorter length or less, but bond strength should have been increased, right? Because they are inversely related. But here bond strength is also weak or less. So that's where the reason is due to electron repulsion. So what I mean to tell here is bond dissociation enthalpy. Which is nothing but amount of energy required. Bond dissociation enthalpy is nothing but amount of energy required to break the particular covalent bond. That's where we have the bond dissociation enthalpy. All of you have understood? Fine. So bond dissociation enthalpy of fluorine is once again very less. That means very less energy is required to break the bond present between the fluorine atoms in a fluorine molecule compared to chlorine molecule. All of you have understood? Fine. So now if I want to brief it out, I will come to another important concept related to this. But before going for that, I'll come to one important, whatever we have discussed, I will summarize that one so to avoid the confusion. Now, due to the smaller size, see one concept or one reason, it will make so many properties of fluorine to be different from other halogens. So, smaller size will make fluorine highly electronegative. Right? I am talking about fluorine. So, smaller size of the fluorine will make highly electronegative element. Smaller size of the fluorine will make low bond dissociation enthalpy. Low bond dissociation enthalpy. Now, what is the actual reason? That is due to electron repulsion. Alright? So, smaller size of the fluorine will make low negative electron gain enthalpy. Or to tell in a general form, we can tell that fluorine is less efficient in accepting the electron compared to chlorine. We are dealing with atoms, okay? So this is related to molecule, as a molecule. So low bond dissociation enthalpy in fluorine molecule due to the electron repulsion. So highly electronegative, that is related to atom. Low negative electron gain enthalpy, that is related to atom. Fine? All of you have understood? So what else we have discussed? Another one is high ionization enthalpy. High ionization enthalpy. So these are the things which we have discussed related to fluorine, which make it differs from other elements. That's why anomalous property. It makes differ from other elements. So this one and this one is related to atom, fluorine atom, and this is related to fluorine molecule. All of you have understood? That's what we have discussed all this time. As a fluorine atom and chlorine atom, if I consider, electron gaining will be dominated by the chlorine as an atom. Chlorine is going to dominate over the fluorine atom when it comes to electron gaining. All of you have understood? Fine. So now we have one important point here, that when I am telling chlorine is highly smaller size, fluorine is smaller size, due to that it will be having less electron gain enthalpy, low negative electron gain enthalpy, but still when it comes to oxidizing character, fluorine F2 is going to dominate. If you recollect redox reaction, there was one chart which was given. In a redox reaction, there was one chart. Same thing will be repeated in electrochemistry, second year also, same chart. So where they will be talking about redox potential. If you observe it carefully, fluorine will be at the top, then lithium will be at the bottom. Lithium will be having highest positive redox potential value, and fluorine will be having highly negative redox potential value. Both are at different terminal. So that shows that fluorine is highly oxidizing. How it's possible? When it comes to electron gain enthalpy, chlorine is going to dominate, but still when it comes to oxidizing character, fluorine is going to dominate. And now I am talking about fluorine molecule is highly oxidizing in nature. That is because when we are talking about halogens which are in diatomic form, now if they are in gaseous state, okay, fine. First thing what will happen is separation of these molecules. First thing is separation of these molecules. There will be breaking of the bond will take place. Alright? So this is nothing but bond dissociation enthalpy. So this is nothing but bond dissociation enthalpy. Now fluorine, if you consider fluorine molecule, they have become fluorine atom, fluorine atom. If you consider chlorine molecule, they have become chlorine atom, chlorine atom. Now, next one is, they are going to accept the electrons. They are going to accept the electron. That's where we have X minus. That's where we have the X minus. So, right, that's where we have the X minus and X minus. They have accepted the electron. So each atom with one electron. Now this will be called as electron gain enthalpy. This is nothing but electron gain enthalpy. So that's where bond dissociation enthalpy, electron gain enthalpy. Next one is, if you observe carefully, ions, I have mentioned it as gaseous state, right? But immediately they will be dissolved. They will be dissolved in water, aqueous form. So that's where X minus aqueous plus X minus aqueous, they got dissolved in this solution. So that's where aqueous form. Now when I am talking about this condition, aqueous form, so this can be called as, any one of you, this can be called as ion getting solubilized. This is nothing but hydration enthalpy. This is nothing but hydration enthalpy. Right? Now if you observe carefully, we have total 3 thermodynamic terms. One is bond dissociation enthalpy, next one is electron gain enthalpy, and next one is hydration enthalpy. Now, if you observe it carefully, chlorine is going to dominate. Chlorine is going to dominate only in this particular form, means in this particular thermodynamic form. Only that chlorine is going to dominate. But fluorine is going to dominate at 2 points. Fluorine is going to dominate at these 2 points. So what I mean to tell here is, although chlorine is having highest electron gain enthalpy, means high negative electron gain enthalpy, but when it comes to bond dissociation enthalpy, fluorine is going to dominate. That means very less energy is required to separate them, and even very less high amount of energy will be released when they are going to mix with the water. Got my point? So the answer should be, why although electron gain enthalpy of fluorine is low compared to chlorine, but still fluorine molecule is highly oxidizing compared to chlorine molecule. The answer is very simple. That is due to low bond dissociation enthalpy and high hydration enthalpy. Means it can easily go with the solution. High amount of energy will be released. That's where we have the hydration enthalpy. So why fluorine is highly oxidizing? First point is low bond dissociation. So low bond dissociation enthalpy. Low bond dissociation enthalpy, and here high hydration enthalpy. High hydration enthalpy. What is hydration enthalpy? It is the amount of energy released when 1 mole of molecule or ions is going to mix with the water or solubilized in the water. That's where we have the condition. So these 2 points should give the answer. One is low bond dissociation enthalpy, and another one is high hydration enthalpy will make fluorine molecule to be highly oxidizing compared to chlorine. This is bit important. Fine. All of you have understood? All of you have understood whatever I have told? Huh? Now you have to remember this one, because this one we are going to discuss in anomalous properties also. All of you have discussed, all of you have understood? Shall I move to the next one? Oh, no answer? Okay, so I got the answer. Okay, fine. So in that case, we will move to the next. So what is the physical state of fluorine at room temperature? Gas. What is the physical state of iodine at room temperature? It will be solid, iodine. So all these things you should remember. Which is the radioactive element in group 17? Astatine. Right? So those things you should remember. Now we will move to the next one. Next one is related to anomalous properties of. Next one will be anomalous properties of fluorine. Anomalous properties of fluorine. Now, when it comes to anomalous properties of fluorine, this concept can be divided into two as usual. First one will be reasons. Right? So it's a repetition. Whatever we have done for oxygen and all, same thing. So what is that first point you are going to write here with respect to reasons? What will be the first point you are going to mention? What is the first point? Smaller enthalpy, smaller size. Kritik, very good. Purnima, very good. Bhavani, I am not getting what you have written. Enthalpy you have written. Okay, very good, all of you. First point should be small size. Due to small size. Right? Okay. So, Bhavani, I think she wanted to tell about bond dissociation enthalpy. So that should be second point. Low bond dissociation enthalpy. Low bond dissociation enthalpy. Where? In fluorine molecule. Low bond dissociation enthalpy in fluorine molecule. Yes. Someone had written absence of d orbital. Very good. So absence of d orbital in the outermost shell. In the outermost shell. Absence of d orbital in the outermost shell. Right? Any other answer? High electron gain enthalpy. One is high electronegativity. That is fine, very good. High electronegativity. Okay. Now this is not high electron gain enthalpy. It should be low negative electron gain enthalpy. Okay. So low negative electron gain enthalpy. Fine. Okay. Even you can tell high hydration enthalpy. You can tell high hydration enthalpy with respect to fluoride ion. High hydration enthalpy. High hydration enthalpy with respect to fluoride. With respect to fluoride. High hydration enthalpy with respect to fluoride. Yes, very good, Sanjana. Yes, high hydrating enthalpy. Fine. So that's where we have the reasons. So Bhavani. Yes, you are absolutely right, Bhavani. That's what I was telling. The reason is low bond dissociation enthalpy and high hydration enthalpy. Fine. So that's where we have the reasons. Reasons for the anomalous properties. Now we have to discuss about which are those anomalous properties, right? So which are those anomalous properties? Now the first one, if you remember atomic size, you can easily give the properties also. So first one, it will be always shows -1 oxidation state. Always shows -1 oxidation state. Done. No positive oxidation state. It's a big box. So therefore always -1 oxidation state. Right? Next. Okay, high standard reduction potential. That one we will not write it here, but that is fine. But we will not write it here. Not high standard, low negative reduction potential. It will not reduce. It will oxidize. It should be very low. Means negative value. Fine. So when it comes to next one, that is one we have written as -1 oxidation state. Yes, we can write it as fluorine is a highly oxidizing molecule. Highly oxidizing molecule. Very good. Right? So what is the reason? Low bond dissociation enthalpy. We have written in the reasons. And high hydration enthalpy. We have written in the reason. That's where we have the property for those reasons. Right? So fluorine molecule is highly oxidizing molecule. Next, another one is due to its low bond dissociation enthalpy and due to its high hydration enthalpy, most of the reactions involving the fluorine will be exothermic. Most of the reactions involving fluorine will be exothermic. So, most of the reactions involving fluorine will be exothermic. Okay, so that should be another one, anomalous property. Next, it will show only one type of oxo acid. That one we are going to discuss. It will show only one type of oxo acids. Acid, not acids. It will show only one type of oxo acid. So that is hypofluorous acid. That is nothing but hypofluorous acid. HOF. Hypofluorous acid. Only one type of oxo acid it will show. But all the other halogens will show more than 1, 2. They will show. But this one will show only one type of oxo acids. Fine? So that's where we have another anomalous property. Now, another anomalous property with related to compound of fluorine is, for example, hydrogen fluoride. Hydrogen fluoride is liquid at room temperature, and other hydrogen halides are gases. Especially if I take HCl, they are gases. So this can be the reason. I will mention. Hydrogen fluoride is liquid at room temperature. This is not liquid. Okay? So hydrogen fluoride will be liquid at room temperature. What is the reason? Reason is very simple. Due to high dipolarity, they can have the hydrogen bond. So due to that, they will be liquid at room temperature. Intermolecular interaction will be more in hydrogen fluoride solution. All of you have understood? So these are some of the anomalous properties of fluorine. Any doubt? So anomalous properties of fluorine, it is also very important. Okay? Any of these anomalous property you can expect. Maybe with related to fluorine, related to oxygen, or related to nitrogen. Any of these three you can expect. Fine? So they can ask as reasons or they can ask as properties. Okay? So now based on the marks you should decide. If it is for 2 marks, don't write all these things. If you write also no problem. But to save the time, for 2 marks you can mention 2 to 3 points. That is more than enough. Fine? So whether I am clear? All of you have understood? If you want some more anomalous properties I can explain. But for time being, these are the things which you can remember. Okay? Now I will come to some of the reactions. I will come to some of the reactions. Someone had written something, 1 minute. Liquid due to strong okay, Bhavani, yes. Due to the intermolecular hydrogen bond. So which is due to high electronegativity of fluorine. Okay? So that's where we have the condition. Fine? So now with respect to reactions, chemical properties. With respect to chemical properties. Now many reactions I am going to tell which you can include in the anomalous properties of fluorine. You can include even these things. Okay? Whichever you remember, that one you can write it down. Now, one of the very important one here is when it comes to fluorine. When it comes to fluorine, when it reacts with water, product will be hydrogen fluoride. Normally hydrogen fluoride will be dissociated form. It will be present as H plus F minus, but anyway, I have written as hydrogen fluoride, and another product will be oxygen. If you observe it carefully, fluorine in zero oxidation state, elemental form, oxygen -2, but in the product, fluorine is -1, oxygen is 0. Poor fellow hydrogen, everywhere it is +1, right? So that's where we can see the oxidizing character of fluorine. Even it can oxidize the oxygen. That proves that fluorine is much more electronegative compared to oxygen, right? So that's where we have the one of the anomalous property. Why? You will come to know. Because when I am talking about chlorine, when it is reacted with water, when it is reacted with water, it's going to form hydrogen chloride. Now you people will be telling, what is that difference, sir? Here hydrogen fluoride, here hydrogen chloride, but another product is not oxygen. It will be HOCl. What do you mean by HOCl? Any one of you, I will see whether you people have observed. What do you mean by HOCl? Related compound we just discussed 2 minutes back. What do you mean by HOCl? Any one of you? Similar compound. I am not telling same compound. Similar compound 2 minutes back we have discussed. Any one of you? What do you mean by HOCl? Okay, that is hypochlorous acid. I discussed about hypofluorous, right? So this is nothing but hypochlorous acid. Anyway, we are going to discuss all these things in detail. So that's where we have the hypochlorous acid. There is no oxygen. Oxygen will okay, we have to balance it, right? So fluorine is 2, 2. Okay, fine. Here it will be 2. So in that case, this one should become 4 and this one should become 2. First equation is balanced. Second equation, oh, student friendly. Already it is balanced. It is student friendly. Now when it comes to bromine, when it is made to react with water, it will form HBr plus HOBr. That is hypobromous acid. If you observe it carefully, chlorine is 0, oxygen is -2, chlorine is -1, oxygen will be -2. That means chlorine should be +1. Same logic here also. Bromine is 0, oxygen -2, bromine is -1, oxygen is -2, bromine is +1. What it indicates? Any one of you, what it indicates? These reactions, what they indicate based on that product, based on the oxidation state in the product, you should tell me what they are going to indicate. Fast. That's where there is a difference between fluorine and other two halogens. Fluorine and other two halogens. Now I will make one point clear. Even iodine can show the similar reaction, but iodine, due to its non-polarity, it will be very less miscible with water. It can go easily with organic solvent, iodine, but it will not go with water. But still, if you force to go with water to react, then the same type of product will be formed even for iodine. Once again I will repeat. So when it comes to iodine, they are very less soluble in water. They can easily go with the organic solvent. That is very important. So therefore when it comes to reaction with water, iodine in most of the cases is not going to react with water. Fine. So due to one of the reason is due to solubility problem. So there is no question of interaction of water with iodine. But if you make them to react, same reaction will happen, but it will be reversible reaction. So iodine is very less reactive with water. But if you make them to react, then the same type of products will be formed. That's where I told another anomalous property of fluorine. Example, you told highly oxidizing agent, right? This is an example for that, where it is oxidizing oxygen, right? Which is coming -2 to 0. But no other halogens, they have the capacity to oxidize the oxygen, right? They are not disturbing the oxidation state of oxygen. That shows that when it comes to electronegativity, oxygen is big boss compared to chlorine and bromine, right? That's what this product tells. So oxygen is -2, oxygen is -2. No change in the oxidation state of oxygen. But chlorine, yes, from 0 it has become -1 without disturbing the oxygen. Okay, but when it is bound with the oxygen, they will take the positive oxidation state. Fine, but fluorine, as usual, it's a big boss. Fine, all of you have understood? Any doubts? Now, instead of iodine, if I take iodide, instead of iodine, if I take iodide, now this iodide can react with the oxygen. This iodide can react with the oxygen, and it should be done under acidic condition. That means I am talking about hydrogen iodide. Hydrogen iodide reacting with the oxygen. H plus I minus is nothing but hydrogen iodide, acidic condition. Now what product you expect? What product you expect? Iodine already it is there, but to make you understand, iodide minus 1, oxygen is 0. So what you expect? Hydrogen, leave it, poor fellow. It will be always in plus 1. Under this condition I am talking about. So what do you think? What should be the product? Sanjana, for what? Yes sir. I want product name. What is that product you expect? Oxygen is more electronegative compared to iodine, no doubt. No doubt at all. So what it will do is, oxygen will force the iodine. No force also. Oxygen, when it is there, iodine, by itself it will donate the electron. Because big boss is there, right? So that's where iodide will get oxidized to iodine. Iodide will get oxidized to iodine, and another product will be water, where oxygen will go to -2 oxidation state, right? So 2 iodide I will make, don't write. So we have to balance the equation. Okay, in that case I will make it as 2H2O because 2 oxygen is there. This one 4H plus. So whether it is balanced, whether it is balanced, we will go with reaction. Means it's donating 1 electron. So here it is donating 2 electrons. Right? So oxygen 0 to -2. That means it is accepting 2 electrons. Oxygen is accepting 2 electrons. So according to this 2 iodide, if I take, it's donating only 2 electrons to become iodine. But according to this equation, oxygen is taking, because here 2 water means 2 to the 4. No, it is not balanced with respect to electrons. We will see. Okay, we will see. Okay, another 2 minutes. Now that's where iodide is getting converted into iodine. That means 2 iodine is there, so 2 iodide. So 1 electron, 1 electron. So total 2 electrons is there. They have lost 2 electrons. So oxygen from 0 it is becoming -2. That means total accepting electron is 2 electron. But since there are 2 oxygen molecule, here also should be 2 oxygen molecule. So in that case, how many electrons? Then it should be 4 electrons. Because 1 oxygen atom taking 2 electrons to become O-2, oxide. But another oxygen atom is also there. Therefore, total 4 electrons, right? So I have to multiply this one by 4 and this one by 2. So in that case, for time being I will write it as 4 iodide plus 2 oxygen plus H plus, giving rise to 4 iodide. So it will become 8. 4 iodide plus Here it will be multiplied by 2, no? 4H2O. Right? Now whether I am right? So here 8 minus is there. So I will make it as 8H plus. Yes. Now it's fine. Now it's fine. Okay? Now we can reduce this to half of. Each one you can reduce to half of. So wherever 8 is there, you can make it as 4 iodide. Wherever 2 is there, you can make it as O2. Or you can keep like this also, no problem. You can keep as it is, or you can make it as half. So 2I2 plus 2H2O. That's where we have the reaction. Once again I will tell, this is also fine, this is also fine. So since here we can reduce to half, that's why I am reducing it. Lower number. Okay? So that's where we have the balanced equation. Fine? All of you have understood? Any doubts? Any other doubts, Sidya? So what I mean to tell here is fluorine with water, it will oxidize the oxygen to oxygen molecule. Chlorine with water, without disturbing the oxygen, it will get reduced to HCl, that is Cl minus. Then oxygen will remain as it is. But chlorine, one other condition, will become positive. Same logic is applicable for bromine also. But when it comes to iodine, it is very less reactive with water. If you force them to react, then similar type of product you are going to expect. Or if I take iodide, they are going to react with the oxygen molecule to form iodine molecule and water, where oxygen very easily it will oxidize iodide to iodine, and itself it will get reduced to -2. So that's what these reactions talks about. All of you have understood? Any doubts related to this? Okay, fine. So I will stop here. If you have any doubts, you can raise the questions. Any doubts? Okay. So in that case, take care. Bye. Tomorrow we are going to continue the class. Take care. Thank you. Thank you everyone. Oh, it's there. Okay. Rajwal, okay, I was not able to see the message. Fluorinating agents in chemical properties I will tell you. Don't worry, I will tell you. Okay? Bye. I don't know.